Yeah. So in the previous few lectures, we were talking about a practical Opamp. So I said the companies which sell you this Opamp ICs, the one that you guys are aware of is MUA741. In fact, a lot of companies like mainly TI and ADI, Analog Devices and Texas Instruments, they sell you a host of uh, Opamp ICs. Okay, mainly they're all 8-pin ICs. They will sell you that, you will find it in the market, and their price ranges can also vary from few cents to few dollars or even tens of dollars. And what distinguishes them? How do you actually use them in your applications? How do you pick the right Opamp for your application? That is of more importance for circuit designers. The course analog electronics doesn't concern with the design of integrated circuit amplifiers. We don't care about IC design amplifiers. This is mainly concerned about designing at a system level, mainly for say embedded system designers, or even analog designers. If you're testing your chip, you're building a motherboard and all that. So this course will help you understand how do you pick the right components. And so for that, you need to understand the theory and also the non-idealities of the components that you're purchasing. Okay. And what are non-idealities? Non-idealities are those properties of amplifiers which deviate them from their nominal behaviors. What are nominal behaviors? Ideally, you want your op-amp to have infinite bandwidth. You want your op-amp to have infinite loop, infinite gain, okay, infinite input impedance, zero output impedance. These are the things you want. But in reality, none of this holds true. Your gain will be finite. Your gain into bandwidth product will be finite. That tells you certain things. Okay. So how do you read that? How do you characterize that? That's what we have been talking about in the previous few lectures. We said that when you plot the frequency response of an op-amp, you get two information from this curve. What do you get? The first one you get is the DC gain. You can read the DC gain from the frequency response curve. The second thing which is of importance, that an op-amp designer, before they ship off a product, there will be a set of engineers who will be characterizing these op-amps. Okay. And they will then provide a document called as data sheet, which will be used, which engineers, students, they will all use it to understand the characteristics and properties of this op-amp. Okay. So this graph shows you the frequency response characteristics of an op-amp. Okay. Open loop frequency response characteristics. So from this graph, I said we normally read the DC gain. We can also read the gain bandwidth product, or it's also called unity gain frequency. And why did we say UGB? What is the importance of UGB? What does UGB tell you? For a circuit designer, if you read, okay, you have certain value, let's say your UGB happens to be 10 megahertz. What does that tell you for a circuit designer, for a system designer? If you're going to use an op-amp with a gain bandwidth product of 10 megahertz, what does that tell you for a circuit designer? What information does that give you? We discussed this, right? This is the maximum frequency until which you can apply and expect the op-amp to give you predictable outputs. What happens if you apply an input of 100 megahertz? What do you expect to see in an op-amp circuit? So let's say I build a very simple, okay, I build a very simple inverting amplifier with a gain of say 100, R2 by R1 is 100. What do you expect will happen after 10 megahertz? If I measure the frequency gain at this point, the gain will decrease, right? Because the open loop gain itself decreases. The circuit is no longer in negative feedback. It is in feedback, but the loop gain is reduced, lower than 1. If your loop gain becomes lower than 1, then you can say that the feedback is very weak. Your feedback is very strong if your loop gain is much greater than 1. So once your loop gain becomes smaller, you lose all those properties. You are banking on loop gain to be very high, so that the closed loop gain is more or less just dependent on ratio of resistors. All those properties will just go away. So your gain will also start decreasing as with increasing frequency. Okay. So that's the information you get from the UGB. So therefore, if you say that you want to build an amplifier or a buffer for an application where you know that the maximum input frequency. So for example, let me give you a simple example. You are designing for audio amplifiers. Do you think an op-amp whose UGB is 10 megahertz, will it work for an audio amplifier application? What is the maximum frequency in audio for audio op-amps? Yeah, in the order of tens of kilohertz, right? So therefore, this should be fine. At 10 megahertz, the gain bandwidth product should be you should know that it's a pretty safe number. So I can use an op-amp with a UGB of 10 megahertz without any problems. Okay. So this graph here, I've taken it from one of the data sheets. I think this is from TI, an op-amp of TI. So you can see they have given you both gain and phase plots. Since I'm assuming at least in your projects or somewhere, you must have done an AC analysis to get this plot. So you can see here from this graph, the UGB, this is the point where the 0 dB line crosses the gain, which happens in around 40 megahertz or so. Okay, 35 to 40 megahertz is where this 0 dB line is crossing it. So you know the UGB. You also know the DC gain here. Okay, so DC gain helps you in case if your input signals are like, for example, if it is being used in a weight measurement. In a weight measurement system, once you stand on top of a weighing machine, your weight is not going to change, right? So it's like a DC input. So you are going to wait for a second at least, right? So when I say DC doesn't mean it has to be constant for all time. For a circuit, let's say you're expecting output out of the circuit within a second. Let's say 1 or 2 seconds, you stand on a weighing machine and within a few seconds, you get your output. For that system, 1 second can look like infinity, right? Because it's producing outputs within a second. So 1 second can look like a very long time for the circuit. So it'll look like DC, like a DC input. So your weighing machine, initially you stand, it'll stabilize and reach a stable value. Then this voltage signal will then be converted to a digital signal and all that. Okay, so that's how your weighing machine displays your output. So for a weighing machine, what matters, because your input signal is DC, what matters is your DC gain. So your DC gain should be very high. And if I want very precise amplification of this signal for this weighing machine, then I need a very high DC gain. Okay, so this is something for you guys to keep in mind. Yeah. So I'm shown here. This is a plot I've taken from a data sheet of I think TI opamps, just showing you how a plot looks like. And why is this useful to you? Because of as a circuit designer, if you want to pick the right amplifier, you need to know what its UGB and DC gains are. DC gains help you if you want very high, accurate, very precise gains, right? We discussed that the sensitivity, the variation in the gain delta A by A is inversely proportional to the DC gain of the op-amp. Okay, so higher the DC gain, you know, the more precise your closed loop gain is. So that's one example. Yeah. The second one, which we discussed in the previous lecture, is offsets. We said offsets can be modeled as an input voltage source at the input of the op-amp. Okay, and on a transfer characteristics, offsets will look something like this. So ideally, you would want an op-amp to transition at the zero crossing point. When your differential voltage is slightly greater than zero, it will go to plus 15, or slightly less than zero, it will go to minus 15, and so on. That transition point, because we are modeling this as a voltage source, that transition point will be shifted. And we said offset voltage can be both positive and negative. And this offset information, the offset voltage, will also be given in the data sheets. So usually they'll mention you what is the maximum offset voltage that you can have. Usually it will be in the order of hundreds of microvolts for general purpose op-amps. And for very good quality op-amps where they have to be used in very precise applications, okay, where your input signal levels are very low, then you need very low offset levels, maybe less than 10 microvolts. So then for those special purpose op-amps which will give you very low offsets, they will cost a bit more, but they will give you very low offset levels. Okay. And I also very briefly told you guys that this is actually the offset voltage distribution. I told you they'll, since offset is a random number, it can be both positive or negative. So what they'll normally do is they'll take a sample. Here in this example, they have written a sample size here. So they have written they have taken 1,400 samples, Opamp chip samples. And then for each Opamp, they will measure this offset voltage. And then they'll plot this. You will have this offset versus the input offset voltage and a histogram plot. So you can see on an average, many products will have what will be the mean value of this and how much is the distribution, how much is the spread. You will get a rough idea by how much your offset voltage will be spread. And based on that, we can take few sigmas as our maximum offset voltages. Okay. And most of the products generally, so you must have studied Gaussian distribution. Many products that you see in practice, when you plot this mismatches and all that, they'll tend to have a Gaussian distribution. Okay. So usually it will be few sigmas, and we will report that as the offset voltage, few sigmas away from the mean values. Okay. So, and this is also, I've taken this data from a data sheet. You can get this information by looking at a data sheet again. So why is offset important? I'll explain it through a very small example. We have already discussed this in the previous lecture, but I'll just reiterate it once again. We said that, let's say you have an input signal whose input levels are in the order of plus minus 10 microvolts. Okay, your minimum input signal is minus 10, maximum is plus 10 microvolts. Okay, it may be a sensor which is producing this output. Okay, it may be a biological, it may be an application in biology. It can be a simple weight measurement system. Okay, it can be some pressure sensor. So anywhere you are producing, it can be even some piezoelectric, like a microphone. This voltage signal happens to be a very small voltage signal, which is between plus to 10 microvolts. I have an ADC. Eventually, I have to feed this signal to an ADC. It turns out the ADC's range is plus minus 10 volts. The ADC can operate on plus minus 10 volts range. So now I have to convert this plus minus 10 microvolt range to plus minus 10 volt range. So what is the total amplification factor needed? I have to convert plus minus 10 microvolt to plus minus 10 volt. So you will need an amplification factor of 1 million, which is 10 power 6. So which is why I've cascaded two inverting amplifier configurations. Each one will provide me a gain of 10 power 3. This is 10 power 3, this is 10 power 3. So total gain of the cascade is 10 power 6. Now tell me, what will be the effect of offset on this? Let's start with the first guy. Let VOS1 be the offset voltage of the first guy. By the time this signal comes to the ADC's input, what will be the voltage here due to the offset? Can you guys analyze this? We analyzed this in the last class, a circuits like this. Can you tell me what will be, so you can model your offset as an input voltage source like this? And can you tell me what will be VOS1? What will be the voltage at this point due to VOS1? The input of the ADC. I'm talking about this point here. Okay. This is the point I'm interested in. This is VOS1. I've given you the feedback resistor values. Approximately, you can give me a rough number. By what factor will this signal be amplified? Offset be amplified? So you're right. So one of you said 10 power 6. That's right. So if you see, right, you can apply the principle of superposition. If you apply principle of superposition, assume your input is 0. If you assume your input to be 0, the first stage will act like a non-inverting amplifier. So your offset will get amplified by a factor of VOS1 into 1 plus 10 power 3. So the first stage will be amplified by 1001 times. Again, the second stage is an inverting configuration, which will amplify it further by another factor of 10 power 3. So totally, roughly the signal will be amplified. What you will get here is minus VOS1 into 10 power 6. So now you see the problem, right? If let's say your offset voltage is 100 microvolts. If I tell you the offset voltage is 100 microvolts for this op-amp, what can happen is that this 100 microvolts multiplied by 10 power 6 will give me 100 volts. This can be plus minus 100 volts. See, it's offset, right? Every op-amp will not have the same 100 microvolt offset. As I said, it will be a distribution. Some op-amps may have higher than 100 microvolts. Some might have lower than that. That's a distribution. But we'll take some 3 sigma value and say that, okay, this is going to be the rough offset. Okay, I'm using the word 3 sigma value. You guys understand what do I mean by 3 sigma or 6 sigma values, right? So if you have a Gaussian function, this is sigma tells you how much it is spreading around the mean value. 6 sigma will be almost 99%, more than 99% spread. So if you design your systems for, let's say I tell you that this is your characteristics of a or a noise or some non-ideality of the system, usually we'll take few sigmas, for practice we'll say and say, okay, if your design meets within 3 sigma, then you know that your design is robust. You don't have to worry about it in the real world. It will work no matter what. Okay, so now I'm saying 100 microvolts is your offset voltage. Even if you forget about this 6 sigma graph, let's assume 100 microvolts is your offset voltage. At the output of the op-amp, it's going to manifest itself as a 100-volt signal. So what do you think will happen at this point? What will happen to this op-amp's output, the second op-amp's output? Assume that the second op-amp is operating on plus minus 15 volts. So this is plus minus 15 volts. Then you can see that the second op-amp output will saturate. It will stay stuck at minus 15 volts forever. Even if your input signal is changing, it doesn't matter. Even if your input signal is changing, the second stage will have some variations. Okay, because of the input signal getting amplified, it will have some variations. But the first stage output will have some variations, but the second stage output is saturated. This is one big problem of offset voltages. Okay, especially they are a big problem if your gain happens to be very high. Offsets can even saturate the amplifiers in the final stage. Okay, so therefore you have to ensure that the offsets are low enough. So let's assume for the second op-amp, let's assume the second op-amp's offset is 100 microvolts. What will be the impact of the second op-amp's offset? What will be the DC voltage of the output due to this second op-amp? What do you guys think? Let's assume 100 microvolts is the second op-amp's offset. What will be the impact of that? Let's assume first op-amp is no offset, 10 power 3 times roughly, right? So which is nothing but how much? 100 plus 100 millivolts, not minus. It's in the non-inverting configuration. So it will be plus 100 millivolts, which may be still okay. In some applications, maybe you can survive with a DC offset. Okay, so you're applying a plus 100 millivolt DC offset, which may be still fine. So if you were to pick as a designer, you are now to pick op-amps for these two amplifiers. And I'm giving you data sheets. And I tell you that one of the op-amps, the available op-amps, one of the op-amps has a 0.1 microvolt the offset voltage. Other op-amp has 100 microvolt offset voltage op-amp. Okay. The first op-amp, you will ensure that always has a very low offset because it's going to see the maximum gain. Okay. So that's how you choose your op-amps from data sheets. So from the data sheet, you get this information for offsets. Once you get this offset information, you know that I have to choose, especially in a high gain application where I have to amplify my signal by several orders. I have to be extremely careful with the offsets. Offsets can even saturate the amplifiers. So I'm going to choose the first amplifier with the lowest offset. Okay, that should have the lowest offset. Second amplifier, I can have little bit relaxed offsets because it's not seeing that high amplification. Okay. Or let's say you don't have the money to purchase a very low offset op amp. What can you do now? We discussed in the last class, right? Let's say we don't have money to do to purchase a low offset op amp. You don't have the budget as a student. Maybe you don't have the budget. Then what do you do? So offset nulling, right? So we discussed in the previous lecture that we can apply this thing called offset nulling. So both of them are inverting amplifiers. So you can apply offset nulling at the positive terminal like this. So in case if you couldn't make it to the previous lecture, you can just look at the video. We discussed in great detail about what is offset nulling. So how do you do offset nulling for this? Short circuit your input. Assume you have not applied no input, and then vary this potentiometer till this output goes to 0. Okay. So now your first op amp has been calibrated. Your first op amp is now properly calibrated, or offset has been nulled for the first op amp. Then once this is 0, similarly for the second op amp, vary this potentiometer till the output, second op amp's output is also 0 if your input to the second amplifier is 0. Okay. You do that, then you do individual offset nulling for both the amplifiers. Now you have calibrated the circuit, then you can apply your input signal. Okay. So when you apply 0 input, you have ensured that the second op amp's output is 0. So once that is done, I'm using the word calibration, but what you have done essentially is offset nulling. Once you have done that, then you can apply your input signal. Okay. So that's all. That's how you build the circuit. Otherwise, you purchase, in case you don't have the freedom to change these offsets, then or you it's not very practical. Every time you don't want to keep doing offset nulling, then you just buy an op amp with very low offsets. Okay, some op amps come with very low offsets by design, so they are called precision amplifiers. Both TI and ADI, they have a lot of chips with very low offsets. Okay, they release products with very low offsets. One thing that I missed in this lecture is that offsets, we just treated it like a constant voltage, okay, which is not changing. But in practice, offsets will be functions of temperatures. Okay, so as you vary your temperature from some minimum to maximum value, your offset voltage will also change. Okay, so therefore, even though you did a offset nulling at some nominal temperature, room temperature, if it turns out that the circuit's temperature is prone to variations, it might happen in very high current applications. Okay, if your temperature is prone to variations, then you have to worry about offset nulling. You have to worry about the temperature drifts as well. So then you will have to think of ways of canceling offsets, even in the presence of temperature drifts. Okay, so offsets can vary with temperature. They'll have a slow variation. As your temperature changes, the offset voltage also can change with temperature. That's something to keep in mind. Okay, so maybe towards the end of the lecture, I'll show you guys a data sheet, how it looks like. I'll now move on to another important non-ideality of an op amp, a practical op amp, which is noise. Okay, so far we have discussed DC gain bandwidth, offsets. So these are the three non-idealities we discussed for an op amp. Okay. Yeah, so one of you have asked me a question. If offsets are mentioned in data sheet, can't we insert a negative voltage to negate the offset? Yeah, that's right. That's what we are doing here. These are called offset nulling circuits. That's what we discussed in the previous class, that you just have to apply a negative voltage. Essentially, that's what these circuits are doing. These are called offset nulling circuits. That's what they do. But the problem is, like I said, they won't be able to track the temperature drifts. We discussed in the previous class how to cancel the offsets, and that's exactly what we do. Here we apply minus V offset so that it adds to plus V offset and cancels out. Okay, but it's a manual process, right? Somebody has to sit in the lab and then do this manually, and it's a painful process. Let's say you are shipping a product which uses this Opamp IC, and you are making 1,000,000 product units. Then for each and every product, you have to do this process, right? And that's a painful thing. You don't want that. So instead, choose an Opamp with a low offset itself to begin with. Then you don't have to do it. But like I said, in case you are on a shoestring budget, you don't have enough money as a student budget projects, you want to do it, then yes, you have to do offset nulling. Offset nulling is essentially that, what you're saying, which is apply a negative voltage to cancel out this positive offset impact. That's it. That's all we are doing. We are manually applying. Yeah. So the second thing, which is of importance, is noise. Noise is because of random thermal motion of electrons that can be in the MOSFETs that are inside the op-amps. It can be in the resistors that may be present in the op-amp, or they can be external to the op-amp too. Okay. Now, noise, if you plot noise on an oscilloscope, it will look like this. It will just look like a random signal. And if you take a sinusoid, at every time instant, its value is precisely defined. You know exactly what the value is going to be. Okay. Whereas for a noise, we can't precisely say what value it is going to take at any given time instant. I mean, we can say, but that's going to involve knowledge of too many factors. Okay, you'll have to know, like, for example, it's almost like throwing a dice, right? If you know exactly the material with which the dice is made, the force that you're going to apply using your hand, and the friction between the hand and your die, and then once the die hits a floor or a surface, the coefficient of restitution between the floor and the dice, all that will dictate. If you know exactly all that information, maybe you can predict, okay, maybe the angle in which you are rolling it and then throwing it into the ground, where it's hitting the ground, taking gravity into effect, all of that. Maybe you can exactly predict what the output of the dice is going to be, right? But since it is too involved, we come up with some ways to understand the die throw experiments. We introduce probability. The same way, we can't directly analyze such signals, noise signals, like we analyze sinusoids, right? If you want to analyze sinusoids, we just compute its Fourier transforms. Okay, we say signal is periodic. Let's look at its Fourier series. Okay, but for noise, since it's not a deterministic signal, we use the word called random signals. Again, this is something, a topic of its own to discuss. Okay, we can't spend just a lecture, so I'll very briefly say that for a noise, it's not a deterministic signal, and when you plot its Fourier transform square, so for noise signals, what we do is we plot something called as power spectral density. Okay, we plot something called as power spectral density. Okay, power spectral density tells you the distribution of the power of the signal as a function of frequency. So if you integrate power spectral density, you will get the power. So it's like your Fourier transform, right? What does Fourier transform tell you? If you take your some signal x of t and then compute its Fourier transform, that becomes capital X of f, and then plot capital X of f the whole square, the mod of this, the whole square, then what you get, if x of t happens to be a power signal, then this mod x of f the whole square will be the power spectral density. Okay, it's a distribution of power and frequency. For a sinusoid, because it's a perfectly periodic signal, in the frequency domain, all the power will be just concentrated on a single frequency. So that's why we use impulses, right? Impulse is a function which tells you that all the power is just concentrated on just one single frequency for a sinusoid. For a noise, if you plot, it will have different shapes in the frequency domain. It'll have, it can be flat, it can be just decreasing with frequency, it can be increasing with frequency, and for different profiles, there are different names. If your noise is constant with frequency, we call it white noise. Why is it called white noise? Because if you mix all the colors, you get white. So which means it has all frequencies of same magnitude, which means it has energy at all frequencies with the same magnitude. The magnitude is same at all frequencies. Then there is something called pink noise. Pink noise is a noise which mostly has low frequency content and less of high frequency content. It will decay as a function of frequency. It will decay as 1 over f or f power some alpha. Then we also define violet noise. Violet noise is a noise whose shape will look like this. It can increase with frequency. If you plot its particle density, you can increase with frequency. So similarly, for the noise that we encounter in circuits, the spectral density of noise will typically look like this. Okay. So normally what you plot on the x-axis will be volt square per hertz. And sometimes you plot it in volt square per hertz, or you take square root of this and plot volt per root hertz. That's like plotting Fourier transform. Volt square, if you plot Fourier transform squared, you get volt square per root hertz, volt square per hertz. Okay. And the graph usually looks like this. It will have a region where your noise will be decreasing with frequency. After that, there will be a flat region. So in this region, it's white noise. This region, there is a specific word. This is actually a pink noise, but it's called flicker noise. Okay. So we will probably, in case you guys want, and on a different course, on where we can spend 1 or 2 lectures just on noise, how to characterize them and all that. Right now, my goal is not that. Just want to give you just basics about noise and how is it useful for circuit designers. Because at the end, when you are a designer who's going to pick an opamp, you have to choose the opamp with the right noise specifications. Because if you don't pick the right opamp, then it may fail your application. Okay, it may not work as you intended. So usually all I'm saying is that if you look at this graph will be provided to you by the datasheet, by the engineer will provide you this datasheet as well. And this graph will be present even in the datasheet. You can gather two informations. One is the floor. What is the noise floor here? And what is the noise level here? So usually what they'll do is they won't mention this noise because it's varying with frequency. I can't just give you one number. Instead, what they'll do is they'll give you, let's say this is 0.1 hertz and this is 10 hertz. They will tell you what is the integrated noise in this range. Okay. So they usually, when you look at a data sheet, right, I'll show you guys the data sheet towards the end of the lecture. You will be given two numbers for noise. They will mention you a spectral density level, maybe some x nanovolts per root hertz. Okay, some 1 or 2 nanovolts per root hertz. Okay, they'll mention that. And they will also give you this number. They'll tell you noise integrated in this 0.1 to 10 hertz range. And then they'll give you a number. Okay, so both these numbers will be provided by the data sheet, in the data sheet itself. Maybe do I have a noise profile here? Maybe let me see if I have. Yeah, I have one. Okay. So you guys see this? This one here is a typical, I think it's one of the TI opamps. It's mentioned in volt per root hertz, the units here. And see here, this noise floor is slightly greater than 1 nanovolt per root hertz. And here it is flicker noise dominant. Okay, here it is thermal noise. If I told you, for example, a weight measurement system, which noise do you think will matter for a weight measurement system? Which noise do you think from this graph? Flicker, right? Flicker is a low frequency noise because it's not changing much. So anything that is in the lower frequencies will matter for input signals which don't change much. For example, weight measurement system. Okay, that it's not going to change much, so it will matter. If you are going to use this amplifier in audio range, then you have to be careful. This noise will matter to you. Okay, if I told you that the input signal has energy only from 10 hertz onwards or 100 hertz onwards or 1 kilohertz onwards, then of course, thermal noise will matter to you. Flicker noise won't be a big problem. Okay, so that's how you do it, and then you can pick an amplifier with a lower noise floor depending on your applications. So how do you mathematically model noise? We just input refer the noise and model it as a DC voltage, as an independent voltage source. You can apply it either to the positive terminal or negative terminal. Okay, it doesn't matter. The only difference is it has to be differentially, it has to appear across the op-amp. Okay, so can I model this noise this way? Is this modeling right? Let's say I put this noise on both the terminals. Is this right? Can I do this? Is there a problem with this noise model? If I put noise at both the inputs. So what's the problem? Will this work? Can I do this? Can I say this is how I'm going to model my noise? Is this right mathematical model? So what is the output voltage? No. Look at this. Look at it this way. I am adding. See, it's not double. I'm writing the same voltage source at this point as well. So this will appear like a common mode input. So this is not the right way to model noise. The right way to model noise is that you should apply the noise differentially. Your input should be like this. Pn should appear differentially between these two terminals. Okay. So that's why I should model it only at one input. If I model it at both the inputs, right? What is V plus here? Let's call it, this is V1, this is V2. Your V plus is going to be Vn plus V1 and V minus is going to be Vn plus V2. So the differential input that goes into the op-amp is just V1 minus V2. There is no impact of noise. So I can't put noise on both the terminals. Okay. So mathematically, when I model it, I can put it on either one of the two terminals. As an input referred noise, I can put it on either one of the two terminals, two input terminals. So it's same as modeling offset. There is no difference between modeling offset and noise voltage. Now, keeping this in mind, very quickly, we'll analyze three circuits. Let's say you have built a voltage follower amplifier. Let Vn denote the input referred noise of the op-amp. What will be the output voltage here? It's a voltage follower. Vi is the input signal. What will be the output voltage due to this noise? It's a voltage follower circuit, right? You can use principle of superposition. Assume Vi is 0, then Vn is 0 and analyze it. What will be the output voltage? Vi plus Vn, right? This is nothing Vi because directly it's a voltage follower circuit. So it will be Vi plus Vn. There is no confusion there. You will get a direct Vi plus Vn. Now this circuit. If I give you this circuit, what will be the output voltage due to noise and input signal? This is RF and this is R. What do you think will be the output? Again, the same rules. Apply principle of superposition. Assume noise is 0. If noise is 0, you should get minus of RF by R times Vi. Now let's assume noise is present, but input signal is 0. What will be the transfer function for the noise? Okay, model your input signal, model the noise wherever it is convenient to you. I can model it in series with the minus terminal, or I can model it in series with the positive terminal. Here it is convenient to model it in the positive terminal. So I can simply write noise here. If I model noise at this point, then the voltage gain for the noise is 1 plus RF by R times Vn. No, answer should not change. Ideally, the answer will not change. No, the answer will remain the same, more or less. It should not change. But as I said, it can be modeled on either terminals. Okay, that's what we did for offset. Okay, so we'll come back to that. Let me finish off this lecture and then we'll discuss that. So your Vn at the output will be amplified version plus this, right? It has the same effect as offset as we discussed in the previous class. Now, what about this circuit? Can you tell me what will be the output voltage due to noise and this? Again, model it on the positive terminal. If you model it on the positive terminal, you will get V noise and Vi in series like this. So what will be the output? Can you guys guess what will be the output for this? It's a non-inverting op-amp, right? It's just going to add up in series. It will be Vn plus Vi times 1 plus Rf by R. Okay? Your noise will directly add to the input signal level. That's it. So now, finally, we'll just answer this question alone so that you guys understand the impact of noise on circuits. So I have a 3-stage amplifier like this. Okay? And I'm interested in knowing, as a designer, which op-amp should have lowest noise, which op-amp can tolerate a poor quality noise, meaning poor noise means its noise is very high. So can you guys tell me by looking at the circuit? Let's call this op-amp 1, O1, O2, O3. Which op-amp noise is most critical, means it matters the most in this circuit? So first you can quickly draw the let us assume the noise voltage of the first op-amp to be Vn1, second op-amp to be Vn2. Yes. So one of you said the first op-amp has the most impact of noise. That's right. Why is that? Because the first op-amp's noise sees the maximum amplification. The first op-amp's noise gets amplified by a factor of 10 power 6. Second op-amp's noise gets amplified by a factor of 10 power 3. Third op-amp's noise comes out as it is without any amplification. So it doesn't matter. I can pick up a very cheap, easily accessible op-amp for the third guy. But for the first guy, I have to ensure that the noise is very low. Why is that? Because it's getting amplified by the next stage, subsequent stages. So the noise level can become so high that it can corrupt your input signal itself. It's seeing the same amplification as the input signal. So if your input signal is going to change, so if your input signal is a very weak signal, which is in the order of microvolts, then your noise, the integrated noise, the noise power also should be very low. So you have to pick the first op-amp has to be a really low noise op-amp. Now, I'll just end the class with a very simple question. Can I cancel out noise? See, remember offset, we canceled it out, right? We just put a circuit called offset nulling circuit and canceled it out. Can I not cancel noise also? Can I do that? Is it possible to cancel noise? Yeah. No, not fully, not at all. You cannot cancel noise because it's completely random. So that's the properties of, so when you take, for example, your goal is that, so previously, see, noise has two properties. One is it's fully random, and second, it is changing with time, right? It's randomly changing with time. Okay. So DC, yes, it's randomly changing with time. I mean, see, for example, if noise was a pure sinusoid, that's a fixed signal. Okay. If it's a pure sinusoid, then I can cancel it out. I can always apply a AC signal, which is a sinusoid, and cancel it out. So previously I was applying, using a potentiometer, offset nulling, I was applying some DC signal and canceling it out. Let's say noise turns out to be a sinusoid. I mean, what is an example of a pure sinusoidal noise? Your supply is generated from a 50 to 60 hertz sine waves. Okay, and then usually you will have some DC sine wave to DC, AC to DC converters, and that will contain unwanted sinusoidal terms. Okay, your supply, your even your the supply generator that you guys use in the lab will contain some 50 hertz noise. Okay, unwanted 50 hertz noise. Maybe you can think of a way of canceling out this, because you know there is only noise at one frequency. Okay, you can just keep on adding some signal with the same frequency, but slowly change its amplitude till it cancels out. Okay, you can do that. But because noise is fully random, you don't know its frequency, you don't know its amplitude, nothing is known. Okay, it's completely random, and it keeps changing with time. It keeps changing with time all the time, and that's why you can never cancel noise. Okay, noise. See, again, I'm using the word with caution. There are circuits where we have to come up with ways of some techniques to cancel noise. Okay, we can do that, but it's not easy. It's not very easy. It's not very trivial. It's not like offset. You can't directly cancel it. Okay, we can cancel common mode noise. Okay, so there are some circuit techniques. What we do is that we ensure that your input signal is differential and noise is common mode. So there are techniques to cancel out, but in general, noise is a signal that you cannot cancel out like offsets. Offset is like a fixed. Once you buy your opamp, it has a fixed offset, and it has a fixed offset variation patterns also. It's going to vary with a fixed pattern with temperature. That's why if you know those patterns, you can easily cancel it out. But noise is not that, because it keeps changing randomly and it doesn't have a fixed frequency, so you cannot cancel it. Okay, so I'll stop at this point.